Hello everyone, my name is Sifat and I'm a second year PhD student at the University of California, Santa Cruz. Today, I'll be presenting our work on predicting wildfire using a state-of-the-art deep learning framework in order to reduce greenhouse gas emission. The numbers in this slide will give us an idea about how massive the impact of wildfire is. And this is what motivated us to work on this project. Wildfire is considered as one of the major sources for greenhouse gas emission. Not only that, it is also detrimental to our life as we suffer from poor air quality and incur other economic loss. Fire events are now occurring more frequently than ever, and it is a direct consequence of climate change. From an environmental perspective, around 350 to 450 million hectares of forest are being burnt every year. And if we look at the recent statistics on California, in 2020 alone, roughly 4% of the total area of the state got burned. One of the devastating things that these fires cause is they emit 5 to 30 tons of carbon per hectare that ultimately results in a huge number. Now, let's have a look at how these fires contribute to greenhouse gas emission. Interestingly enough, the greenhouse gas emission from wildfires forms a vicious cycle as it evolves, what you can see in the figure. So, carbon dioxide is the major component of greenhouse gas. We all know that trees capture carbon from the atmosphere. So when they burn, a lot of carbon gets released in the atmosphere. So the more emission results in more carbon, that is a change in the climate and it increases the temperature. As the temperature rises, it makes the vegetation drier, more flammable, and susceptible for burning for a longer period of time. And that restricts the growth of newer vegetation. And in turn, this dry vegetation causes more frequent fires, hence creating a feedback loop of the increased greenhouse gas emission. In order to curb climate change, we need to reduce the incidence of wildfires that shoot up the amount of greenhouse gas in the environment. For doing so, we must be able to accurately predict the occurrences of fire events so that we can take measures for preventing those fires. This is the main objective of our work. For predicting fire locations, we first need to analyze the complex dynamics between different contributing factors and how they lead to a fire ignition. Let's look at the factors. First of all, weather or meteorological factors. The wind, the temperature, the precipitation all have a direct and strong causation to ignite a fire and have a prominent role in determining fire hotspots. Besides that, naturally occurring wildfires can easily be sparked by dry weather and droughts, since dry vegetation acts as a flammable fuel while warm temperature encourages combustion. There are some vegetation indices that can indicate the greenness of an area. Moving on to the next factor, topography, which is an important one that influences the fire behavior of a region. It interplays with the wind speed and direction and impact fire initiation. How? So on the slopes, the wind usually blows up during the day and less dense air, that is reflected by the surface, rises up along the slope. Hence, the steeper the slope, the quicker the hot air will flow uphill and preheat the flammable fuel to its ignition temperature. Thus, the uphill zones are more prone to the fire ignition during the daytime. But in the nighttime, the scenario is opposite when the cooler wind starts to flow downhill. And last but not the least, one of the common causes of wildfire ignition is electrical equipment and power line failures. There can be arcing, line-to-line faults, malfunctioning of transformers, and many such events that leads to a wildfire. In this slide, you can see the full set of features that influences a fire ignition, which we have used to construct our own dataset from scratch. For the weather features, we have used temperature, specific humidity, precipitable water vapor, surface pressure, wind speed from two directions, east and north. NDVI, which is the Normalized Difference Vegetation Index, and EVI, Enhanced Vegetation Index. These are the two vegetation indices that are used. Digital Elevation Model, or DEM, dictates the topography of an area. And finally, we have added the proximity to nearby power lines. The two deadliest fires in California, the Camp and Tubbs, which occurred in Butte, Napa, and Sonoma County, respectively in 2018 and 2017, were selected as the test case for our study. The location of the fire points were obtained from NASA that uses the MODIS Terra product, and the above mentioned features were collected for the fire points as well as for the nearby no fire points in order to construct the dataset. With that, we are moving on to the next part of our work using Conditional Tabular Generative Adversarial Network, or CTGAN, for predicting fire location. First of all, let's talk about why do we even need GAN? So we want to classify the fire and no fire points in the dataset by using different machine learning techniques. But as there are a variety of factors in this task, and they are also related to each other, it is very hard to understand the complex dynamics between these factors and their influence on a fire ignition, where traditional machine learning algorithms are not good enough. That is why we need to use some better techniques. Deep learning is one as such. It's basically some variation of neural network, where deep refers to the number of hidden layers in the network. As the depth of the network increases, the more insights about the prediction analysis can be found. But these techniques are really data hungry. That is, you need to feed a lot of data into the network to reap the benefit. Hence, we need to generate synthetic data from the original set via an appropriate data augmentation technique, which is CTGAN. Before going into the CTGAN model, let's have a quick glance on a basic GAN structure. So GAN is a supervised learning approach which discovers and learns the pattern in a dataset on its own and produces new data samples. There are two main parts in a GAN, generator and the discriminator. Given a random noise, the generator tries to learn the distribution of the data and generate new samples as close as to the real ones. Then these samples are fed into the discriminator along with the real samples to see if it can differentiate between the real and the synthetic or fake samples. The goal of the generator is to fool the discriminator by generating good quality samples until the discriminator identifies them as real. Now, CTGAN, that refers to Conditional Tabular Generative Adversarial Network, is a special variation of GAN. So there are certain limitations that a simple GAN cannot overcome. For example, modeling the non-Gaussian distribution in tabular data. Moreover, it is incapable of doing a mode-specific normalization in a multimodal distribution of continuous columns, which is very common in a tabular dataset. In the figure, we can see the structure of a CTGAN where the main functionality of the generator and the discriminator is the same as before, but there are some pre-processing in the representation of the data before feeding it to the discriminator block. As we have stated earlier, we don't want just enough data, rather we want good quality data that resembles the original distribution of the real data set. This is what the CTGAN is doing. Learning the distribution of the real data, having multiple modes with a variational Gaussian mixture model. Here, beta is the sample mode and alpha is the scalar within that mode. K star is one of the categories in the discrete column. Now, let's have a look at the attributes of our data set in the left-hand side, the data set that we have built. It has 10 features with 2 labels. Those are fire and no fire. In total, there are 849 data points, and we can say it's a pretty balanced data set, right? Where the ratio between the two classes is 1:1.021. Now, let's see how we have applied the CTGAN in our work in the right-hand side. First, we splitted our original dataset into a training set and a test set with the 70:30 ratio. Then we applied CTGAN on the training set to generate more synthetic realistic data that ultimately was used as the augmented training set to train 5 machine learning models, which are decision tree, random forest, gradient boosting machine, support vector machine, and neural network. So here are the results that we got after implementing our idea. So we have named our proposed approach of training the baseline models with an augmented dataset as CTGAN plus baseline, and it is indicated as the red bars. And we have compared the performance of this approach with the baseline models trained with the original training set with limited data. We have used the test accuracy as the performance metric, and it is evident that except for the support vector machine and decision tree, our proposed approach has outperformed all the rest of the baseline counterparts, that is random forest, GBM, and neural network. To bolster the performance of the models, we have also checked other metrics including weighted precision recall and F1 score, and this table shows that for random forest, GBM, and neural network, our proposed technique has improved the score in all 3 metrics. Finally, to fortify the efficacy of our proposed approach, we have evaluated the performance in another dataset that has similar features with the same label as that of our dataset. So the previous 2 slides present the results for using in our own dataset, and this slide presents the data for implementing our proposed approach in another dataset. And it turns out that the overall test accuracy of our proposed approach is higher than the baseline performance in all 4 machine learning models except the random forest. And this is the result for the weighted precision, recall, and F1 score checked for the same dataset, which clearly shows the efficiency of our approach. To conclude, wildfire incidents have increased as a result of global warming, which in turn has increased carbon emission. To curb this emission, we focused on predicting fire locations. In order to achieve so, we propose a GAN-based technique for predicting fire locations by analyzing the contribution of numerous factors of fire ignition. We have used CTGAN to generate high-quality realistic data that helps in boosting up the performance, the prediction performance of different machine learning algorithms. By adopting this approach, we can undertake preventive actions like restricting human activities around the high-risk zones that can easily ignite a large fire. Vegetation management tasks can also be carried out wherever it is deemed necessary in order to minimize the chance of power line-induced fire. By utilizing our approach, we can prevent fire ignition, which will eventually result in reducing greenhouse gas emission. With that, I conclude my talk. I'm looking forward to answering your questions. Thanks for watching.